Hello and welcome. In this video, I'm going to show you how to interpret a few of the results that are produced when you run a multiple regression in Excel. In a prior video, I showed you how to run this regression. Now that we have it, I'm going to show you a few points that you may want to interpret. So at this point, we have our multiple R. That is the correlation that's been measured in this model. We have the two very important R squareds that we are focused on are right here. That R squared tells us the amount of variance that is explained by our regression line. And what that means right here is if we just say, show me the means, we get a pretty flat line. Then we say, well, I'm going to form a regression line, and I'm going to form it based on a couple of variables, and our regression line will look like this. Hopefully that regression line should be able to explain some of the variance, and our R squared says that it's explaining about 42.7 of the variance in comparison to just a flat line. The adjusted R squared becomes very important for us because this is basically saying I want to consider the R squared, but I want to account for, in effect, the complexity of my model. We could say the complexity as the degrees of freedom. Another way to think about that is how many variables are you using in your model. The more variables you're using, the more complex your model. So we can interpret an R squared right now. The adjusted R squared doesn't mean much right now, but it will in just a second when we start to compare different models. Let's go down and consider these coefficients and p-values. The first variable here is always going to be our intercept. And for our purposes with our projects, we're not going to really consider that. We want to consider these independent variables. Basement. This is the square footage of the basement. This is the above ground area, above ground square footage, and the lot size. We can see that for basement, this p-value is well below what we would call the level of significance of 0.05. This is way below. It's a 0.00259. So this definitely meets our threshold for significance. The above ground area is an 8.12, but it's got an exponent of -10. So this is 0.000. There's 9 zeros in front of this 8. This is definitely going to be significant. This lot size, however, this has a p-value of 0.32567. That's way above the cutoff of 0.05. So in this case, we would say that this lot size is not very significant. It's not having a big impact on the variance in our model, in our dependent variable. Basement and above ground area both do have a significant influence on the variance in the dependent variable. Now, I wanted to show really quick, what do these coefficients mean? Well, the coefficients, in this case, if I wanted to make a model of the sale price of the home, I could say that sale price is equal to, well, it's going to be equal to, in some way or another, it's going to be equal to the square footage of the above ground area. It's also going to be some kind of a function of the basement square footage and it's also going to be some kind of a function of the lot size. And our regression tells us in its way how much our sale price will vary when we change the square footage, basement square footage, and lot size. Why those variables? Because those are the variables that we chose to include in our model. So we have an intercept. The coefficient is 368,136. That's our y-intercept, and that means that if everything else were set to 0, we would still have a value of our lot of $368,136. We have a coefficient for above ground. This says for 145.35. What this is saying is for every 1 square foot that I increase the size of the house, I get a $145 increase in the sale price of the home. So every square foot is worth about $145. And you've probably heard something like this when they say the price per square foot of a home. Well, this is saying every time I increase that the square footage of the home, it would increase the value of the home by $145. Here I have basement square footage, and this number right here is saying whenever I increase a basement square footage by a square foot, the value of the home will increase by 69.295. And the lot size will affect my value of my home by roughly 2.485 dollars every time that I add another foot to the lot size, or square foot to the lot size. So if I wanted to know the sale price of a home, my guess based on my regression model is, well, I think the value of the home would start at $368,136. For every 1 square foot that I add to the size of the home, I'm going to increase the value by about $145. For every 1 foot that I increase the basement square footage, I'm going to increase the value of the home by about $69. And every 1 square foot that I increase the lot size, I'm going to increase the value of the home by about $2.49, roughly. This is how I can get my regression equation from the Excel output. Now, I wanted to review or revisit really quick the idea of the adjusted R squared, which is given to us right here. I have another worksheet I'd like to show you. I have a model that only considers a simple regression between the above ground size of the house and the price. I called this model above ground. The independent variable is only above ground, the dependent is price. My R squared in this case is 0.358826-ish. My adjusted R squared is 0.35178-ish. Now, I also have a second model, and you'll notice that I call this one above ground and lot. It considers the independent variables, the above ground square footage, and the lot size. The dependent variable is the price of the home. That's the sale price, not the asking price. My R squared has gone up just a little. You will notice in this case, however, that my adjusted R squared, and I have to go up quite a few digits here, but the adjusted R squared has actually come down. It went from 3517 to 3515. Now that's only off by 2/10,000ths. But the point is, adjusted R squares considers the complexity of our model. Specifically, it looks at the degrees of freedom. You could also say it looks at simply the number of variables that are in the model. Clearly, a model with one independent variable is simpler than a model with two independent variables. Or we could say one independent variable, two independent variables. When I see the adjusted R squared actually go down, what that's saying is the value, the utility that you're getting from lot size is not enough to justify in your model building the complexity of this variable. Now let's look at another model. This is my above ground and basement model. It considers the two variables again, above ground and basement is my independent variables, again, price as my dependent variable. You'll see the R squared has gone up quite a bit. You'll also notice that when I had just a very simple model, one independent variable, my adjusted R squared was 0.35. When I added in basement in addition to the above ground variable, my adjusted R squared went up quite a bit by about 0.05. This tells me that because my adjusted R squared did a very significant jump, or really any jump, this is saying, yeah, you're making your model more complex with this basement variable, but you are definitely getting a significant return on the investment. You're able to explain a very significant amount of the variance in your model. In this case, you can see that the above ground p-value, this is 6.73, but it's got 10 zeros in front of that. And this basement variable has a p-value of 0.00248. These are way below the cutoff of a 0.05. So both of my variables have a very significant p-value. And going back to my model, where when I added the lot size variable, my adjusted R squared actually went down. Well, this is saying that my lot size p-value, this 0.3285, is way above the cutoff of 0.5. It's about 6 times the cutoff value. So that's not a surprise that adding lot size to this model didn't help us. It's not considered to be a significant variable in the model as far as its ability to explain variance in the dependent variable. And it didn't have much effect. It actually lowered the amount of variance that my variables, it's actually lowering the amount of variance in the dependent variable that is explained by the independent variables in my model. Again, I could add another variable here and go with above ground, basement, and lot. My adjusted R squared is actually coming down again. Why? Because I keep including this lot size variable, which has, according to my p-value, it's not helping me. This 0.3256 is way above the cutoff to be significant, which is 0.05. This is a really good example of a model where, and I'm shocked by this, that the lot that the house sits on is not significantly impacting the price of the home. That's very counterintuitive. You would think that the bigger the lot, the more value the home. But in fact, what's affecting the value of the home is the above ground square footage and the basement square footage. Once we account for those, the lot size, according to our numbers, doesn't tell us very much. And that's counterintuitive, but the numbers here are telling us loud and clear lot size is not influencing the price of the home. Now, that's so counterintuitive that I'm going to go ahead and make a comment on that. These houses, it's going to have to do with the neighborhoods that they're in. There's all kinds of other factors that are playing a role in the value or the sale price of these homes. Obviously, the price per square foot of any piece of land plays a factor. It's just that in this case, the size of the home as measured by the above ground square footage and also the basement, those factors are so overwhelming that they're basically knocking out the lot. If you look at our simple regression results, you'll see that the lot size, when we ran just lot size against the price, that R squared, not very high, but our p-value is well below the cutoff. So if we said, look, does lot size affect the price of the home? If all I consider is the lot size, then yes, 0.02 is considerably less than 0.05. It's only when we start to account for other variables in the model that lot size will fall away. And that's how we can look at one way to look at this regression output. Thanks for your time. I hope you have a great day.